Welcome to Derivability. Okay, this is a channel where we take a look at derivations from physics, engineering, calculus classes. Maybe some things that you've seen in class, but I want to see one more time, derived out and proved. Maybe doing a little review. Maybe you're getting ahead. A lot of stuff. So, if you've been to the channel before, thanks for coming back. And today we're going to be taking a look at the radius of curvature of a plane curve, say y as a function of x in Cartesian coordinates. We want to find the radius of curvature given the y as a function of x. Okay, this is most commonly encountered in either like a Calc 3 class when you're doing vector calculus, maybe in a mechanical engineering class like dynamics, where you're interested in particles that are constrained to move in a certain path, and among other things, you need to know what the radius of curvature is along that path. Okay, so let's start with the velocity vector in Cartesian coordinates. Of course, that's the time derivative of the x-coordinate times an I hat unit vector plus dy by dt times the j hat unit vector. Often in physics and engineering, we shorten up these derivatives in the so-called Leibniz format, like written as fractions, to the so-called Newtonian dot notation. So x dot is the v sub x, if you like, or dx by dt. Likewise for y dot. Okay. Now some things we're going to need to know. We know that centripetal acceleration, sometimes called normal acceleration, is v squared over r, but in context we use the Greek letter rho to stand for the radius of curvature. Okay, what we're going to do is we're going to kind of work this backwards and solve this formula for rho as v squared over this normal acceleration, okay, or the so-called centripetal acceleration. Okay. Now we have v up top there, so in terms of v squared, that's just the Pythagorean theorem applied to that vector equation. Okay, we'll definitely get back to that. Okay, now a sub n, the normal acceleration, okay, what we have to understand here is that the acceleration vector has two parts to it. Okay, that is what we call the tangential acceleration, that's parallel or anti-parallel to the velocity as a vector, plus the normal or centripetal acceleration. Okay, so in my picture, okay, let's try and draw what these would be in the picture. Now, if the object were speeding up along the curve, the tangential acceleration points in the same direction as the velocity vector. But if it were slowing down along the curve, it would just point opposite. Either way, it's tangent to the curve, that blue curve, tangent line. Okay. Now, you'll see that in addition to this tangent line, which approximates the curve, I have what we might call a tangent circle, or an approximating circle, which approximates the curve in a slightly better sense in terms of its curvature. And we see the radius of curvature drawn right there. Okay, and the centripetal acceleration, okay, pardon my drawing here, or sometimes called the normal acceleration, points toward the center of that curve. Okay, so you've probably seen something like this before. The nice thing is that these two tangential and normal accelerations are perpendicular to each other. So we can basically take a Pythagorean theorem with these accelerations. Okay, and the way we're going to go about this is we are going to solve for a sub n squared as a squared minus a sub t squared. Okay, looks like we need just a little bit more room. So let me pause the video for a moment and create some room. Be right back with you. Okay, well, we're back. All right, so we know that the velocity vector, okay, so they're written up above. I'll just write it here again. That's x dot I hat plus y dot j hat. Well, we can get the acceleration vector now, the whole acceleration vector, by taking the derivative of the velocity vector. So we just keep putting dots on top of the x's and y's here. So x double dot I plus y double dot j. Okay? And to get the squared magnitude of the entire acceleration vector, well, we're just going to use the Pythagorean theorem on this. Okay, so a squared equals x double dot squared plus y double dot squared. Okay. Now about the tangential acceleration, okay, that points in the direction of the velocity. Okay, so this is the time derivative of the speed, okay, times, say, a unit vector in the tangential direction. Okay. Well, if v equals that expression, okay, and v squared, Pythagorean theorem, equals x dot squared plus y dot squared, then we can take another derivative and get an expression for v dot. Okay, we're going to have to use something called implicit differentiation and the chain rule to keep moving along, but certainly something you probably know how to do. So we get 2v dot equals 2x dot, and then the derivative of that chain rule is x double dot. Okay, and then likewise on for the y variable here. Okay, we get these 2's to very nicely cancel out. Solve for v. Okay, x dot, x double dot plus y dot, y double dot, all over the magnitude of v. Okay, which I could substitute this formula related to that, but we won't need to do that right now. Okay, we'll come back and do that in a moment. Okay, create a little bit more space now. Okay, all right, so now let's go back to a sub n squared, which is kind of where we're at. Okay, that's going to be a squared minus a sub t squared. Okay, now a squared, Pythagorean theorem, was just this x double dot squared plus y double dot squared. Okay, and then I have minus the appropriate expression for a sub t squared, which comes from v dot. Forgot that dot just a minute ago here. Okay, so let's square that. Okay, so x dot, x double dot plus y dot, y double dot over v, all squared. Okay, all right, well, first of all, let's just recognize we need to get a common denominator. Okay, so that common denominator is going to be v squared. Okay, but first I need to multiply that up into the numerator that I would have right here. Okay, and I'm going to use v squared as x dot squared plus y dot squared right here. Okay, all right, otherwise I'm just going to multiply out the binomial in that numerator. Okay, x dot squared, x double dot squared plus 2x dot, x double dot, y dot, y double dot plus y dot squared, y double dot squared. Okay. All right, so next let's multiply out the binomial at the beginning here. Okay, in some order here we're going to have x dot squared, x double dot squared plus x double dot squared, y dot squared. Okay, plus x dot squared, y double dot squared plus y dot squared, y double dot squared. Okay, and now distribute the minus sign through that grouping in parentheses. Let's just remember all of this is going to be over v squared. Okay, so x dot squared, x double dot squared minus 2x dot x double dot, y dot, y double dot, those are all multiplied together, minus y dot squared, y double dot squared. Okay, and we see we're going to get some things to cancel out here, okay, which is very nice. So we have that pair that cancels, this pair that cancels. Okay, so let's kind of copy this down into the next line. Okay, what I'm going to have is x double dot squared, y dot squared. And let me write that negative 2 term next. Negative 2x dot x double dot, y double dot. And then plus x dot squared, y double dot squared. This is all over v squared. Okay. Now if you look at that numerator closely, you'll find that it is a perfect binomial square. Kind of follows that that pattern here. So that is x double dot y dot minus x dot y double dot quantity squared. Okay, all over v squared. Okay, now this, reminder down here at the end, this is a sub n squared, normal acceleration squared. All right, so we can take the square root of both sides. The right-hand side, a sub n, and v down the bottom. Those are magnitudes. Those will be what they are. The numerator will have to be written as an absolute value. So let me create some more space, and then we'll get back to it. Okay, here we are again. All right, so here we are. A sub n equals the absolute value of this difference up here, x double dot y dot minus x dot y double dot, all over v. Okay, and a reminder where we're headed. We want rho equals a sub n over v squared. Okay. All right. Well, let's keep on working with a sub n. Okay. What we have to remember now is that we want this, you know, not in terms of motion necessarily, but from the shape of the curve, the y equals f of x shape of the curve. Okay. Probably not going to surprise you to learn that it has to do with kind of the curviness of the curve. In other words, the derivative of the curve y by dx, what y prime, okay, that's going to be somehow related to y dot. Okay, so let me write that down here. Remember, y dot is dy by dt. Okay, and we can kind of use our chain rule here to kind of fill in some empty spaces. Okay, let's put a dx in each of those empty spaces. Okay, so let's call dy by dx y prime, you know, your good old calculus notation. And then, of course, dx by dt is x dot. Okay, so every place we see a y dot up in the above formula, or any formula here, we can replace it with y prime x dot. Okay, now we're also going to need to know something about y double dot. Okay. And I'll tell you what, I'm just going to shortcut that, and you can verify this on your own here, but this is going to be the same thing as y double prime x dot squared plus y prime x double dot. Okay, that can be achieved from the previous line using the product rule, of course, and the chain rule like we have been doing. Okay. All right, so let's go back to that numerator in a sub n. All right, and let's just see how this shakes out. Okay, so I've got an x double dot. Gets to stay there. And then my y dot is the same thing as y prime x dot. Okay, then I have minus x dot. And then my y double dot, I'm going to replace like this, y double prime x dot squared plus y prime x double dot. Okay, now let's distribute through the parentheses. Okay, so we're going to get an x dot cubed at some point there, and then we're going to get a y prime x dot x double dot. Okay, well, the first and last terms here are identical. They cancel out, don't they? Okay, so what we're left with is the absolute value, okay, I can kill the negative, of y double prime x dot cubed. All right, so we're about on the home stretch here. I'll need to create a little bit more space. Okay, here we are again, got some more space. So resuming where we left off here, okay, my numerator I could write as an absolute value like that. Okay, my denominator v, of course, we know that's equal to the square root of x dot squared plus y dot squared. And we can make a replacement on the y dot there the same way that we've been doing. So the numerator is cubed. Okay, the numerator copies in there just like that. So otherwise I have the square root of x dot squared plus, and then the y dot squared becomes y prime squared x dot squared. So I can factor out an x dot squared from that denominator. And then when I take it out of the square root, it becomes the absolute value of x dot. And then I have the square root of 1 plus y prime squared. Okay, my numerator up there, I can write that as the absolute value of y double prime, and then times the absolute value of x dot cubed. Okay, that leaves me an x dot squared in the numerator, no absolute value necessary, and then absolute value of y double prime, and then over 1 plus y prime squared. All right, finally, or almost finally, now we can write, I get back to our formula for rho. Okay, rho is going to be equal to, rho is going to be equal to v squared over a sub n. Okay, so v squared is the same thing as x dot squared plus y dot squared. And then let's take the reciprocal of a sub n, so I get the square root of 1 plus y prime squared over x dot squared y double prime, absolute value. Okay, all right, and then just one more quick thing here. That numerator, or rather the part that's in parentheses, we just managed that kind of as we did in the previous couple of steps here. I can write that as x dot squared, and in parentheses 1 plus y prime squared. Okay, and then times the square root of the same quantity, and then over x dot squared, absolute value of y double prime. Okay, and we get those x dots canceling out. Okay, and finally the formula we're interested in is rho equals 1 plus y prime squared to the 3/2 power divided by the absolute value of y double prime. Okay, this should match the formula that is quoted probably in your engineering book, dynamics, or your calculus book. Maybe an advanced physics book in the subject of mechanics would have this in there as well. Okay, maybe the notation might be slightly different. This is for a plane curve. Okay, in general, curves don't have to be restricted to a plane. Okay, so there's a more fancy formula if you're not in the XY plane, let's just say. Okay, sometimes those books give derivation, sometimes they don't. Here you go. So hopefully this is helpful, despite my sloppy writing. Okay, thanks for dropping in here. Hope this has been helpful, and hopefully I'll see you in some other videos real soon.